Alright, so this is Chapter 2 of the INCOSE Systems Engineering Handbook. Chapter 2, Systems Engineering Overview. Section 2.1, Introduction. This chapter offers a brief overview of the systems engineering discipline, beginning with a few key definitions, an abbreviated survey of the origins of the discipline, and discussions on the value of applying systems engineering. Other concepts, such as systems science, systems thinking, systems engineering leadership, systems engineering ethics, and professional development, are also introduced. Section 2.1 Definitions and Concepts of a System. While the concepts of a system can generally be traced back to early Western philosophy and later to science, the concept most familiar to systems engineers is often traced to Ludwig von Bertalanffy, 1950-1968, in which a system is regarded as a whole consisting of interacting parts. The ISO, IEC, IEEE definitions provided in this handbook draw from this concept. Section 2.2, subsection 1. General system concepts. Systems considered in ISO, IEC, IEEE 15288, and in this handbook are man-made, created, and utilized to provide products or services in defined environments for the benefit of users and other stakeholders. The definitions cited here and in Appendix C refer to systems in the real world. A system concept should be regarded as a shared mental representation of the actual system. The systems engineer must continually distinguish between systems in the real world and the system representations. The INCOSE and the ISO, IEC, IEEE definitions draw from this view of a system: an integrated set of elements, subsystems, or assemblies that accomplish a defined objective. These elements include products, which might be hardware, software, and firmware, processes, information, people, techniques, facilities, services, and other support elements. That's the INCOSE one. And a combination of interacting elements organized to achieve one or more stated purposes, which is the ISO, IEC, IEEE definition. Thus, the usage of terminology throughout this handbook is clearly an elaboration of the fundamental idea that a system is a purposeful whole that consists of interacting parts. An external view of a system must introduce elements that specifically do not belong to the system, but do interact with the system. This collection of elements is called the operating environment or context and can include the users or operators of the system. The internal and external views of a system give rise to the concept of a system boundary. In practice, the system's boundary is a line of demarcation between the system itself and the greater context to include the operating environment. It defines what belongs to the system and what doesn't. The system boundary is not to be confused with the subset of elements that interact with the environment. The functionality of a system is typically expressed in terms of the interactions of the system with its operating environment, especially the users. When a system is considered as an integrated combination of interacting elements, the functionality of the system derives not just from the interactions of individual elements with the environmental elements, but also from how these interactions are influenced by the organization through interrelations. By the organization of the system elements. This leads to the concept of a system architecture, which ISO, IEC, IEEE 42010 from 2011 defines as the fundamental concepts or properties of a system in its environment, embodied in its elements, relationships, and in the principles of its design and evolution. And again, that was the system architecture, the concept of a system architecture. This definition speaks both to the internal and external views of the system and shares the concepts from the definitions of a system. Chapter 2.2, subsection 2. Scientific terminology related to systems concepts. In general, engineering can be regarded as the practice of creating and sustaining services, systems, devices, machines, structures, processes, and products to improve the quality of life, getting things done effectively and efficiently. The repeatability of experiments demanded by science is critical for delivering practical engineering solutions that have commercial value. Engineering in general, and SE in particular, draw heavily from the terminology and concepts of science. An attribute of a system, or system element, is an observable characteristic or property of that system, or system element. For example, among the various attributes of an aircraft is its airspeed. Attributes are represented symbolically by variables. Specifically, a variable is a symbol or name that identifies an attribute. Every variable has a domain, which could be but is not necessarily measurable. A measurement is the outcome of a process in which the system of interest interacts with an observation system under specified conditions. The outcome of a measurement is the assignment of a value to a variable. A system is in a state when the values assigned to its attributes remain constant or steady for a meaningful period of time. In SE and software engineering, the system elements, by example, software objects, have processes, or operations, in addition to attributes. These have the binary logical values of being either idle or executing. A complete description of a system state therefore requires values to be assigned to both attributes and processes. Dynamic behavior of a system is the time evolution of the system state. Emergent behavior is a behavior of the system that cannot be understood exclusively in terms of the behavior of the individual system elements. By extension, it's the behaviors that happen when the parts interact. The key concept used for problem solving is the black box or white box system representation. The black box representation is based on an external view of the system, the attributes. The white box representation is based on an internal view of the system, where you can see the attributes and structure of the elements. There must also be an understanding of the relationship between the two. A system, then, is represented by the external attributes of the system, its internal attributes and structure, and the interrelationships between these that are governed by the laws of science. General Systems Methodologies, Chapter 2.2, Subsection 3. Early pioneers of systems engineering and software engineering, such as Jordan and Wymore, long sought to bring discipline and precision to the understanding of management of the dynamic behavior of a system by seeking relations between the external and internal representations of the system. Simply stated, they believed that if the flow of dynamic behavior, the system state evolution, could be mapped coherently into the flow of states of the constituent elements of the system, then emergent behaviors could be better understood and managed. Clear, in 1991, complemented the concepts of a system in engineering and science with a general systems methodology. He regarded problem solving in general to rest upon a principle of alternatively using abstraction and interpretation to solve a problem. He considered that his methodology could be used both for system inquiry, i.e., the representation of an aspect of reality, and for system definition, i.e., the representation of purposeful, man-made objects. Chapter 2.3. The hierarchy within a system. The ISO, IEC, IEEE usage of terminology, these system elements, can be atomic, i.e., not further decomposed, or they can be systems on their own merit, i.e., decomposed into further subordinate system elements. The integration of the system elements must establish the relationship between the effects that organizing the elements has on their interactions and how these effects enable the system to achieve its purpose. One of the challenges of system definition is to understand what level of detail is necessary to define each system element and the interactions between elements. Because these systems of interests are in the real world, this means that the response to this challenge will be domain-specific. A system element that needs only a black box representation, the external view, to capture its requirements and confidently specify its real-world solution definition, can be regarded as atomic. Decisions to make, buy, or reuse the element can then be made with confidence without further specification of the element. This leads to the concept of hierarchy within a system. One approach to defining the elements of a system and their interrelations is to identify a complete set of distinct system elements with regard only to their relation to the whole, by suppressing details of the interactions and interrelations. This is referred to as a partitioning of the system. Each element can be either atomic or can be a much higher level that could be viewed as a system itself. At any given level, the elements are grouped into distinct subsets of elements, subordinated to a higher level system, as illustrated in Figure 2.1. Thus, hierarchy within a system is an organizational representation of a system structure using a partitioning relation. And here's Figure 2.1, which represents the hierarchy within a system. It's adapted from ISO, IEC, IEEE 15288, and it is from Figure 1 on page 11 and Figure 2 on page 12, with permission from ANZ. In the top left, it shows a system composed of 3 distinct system elements, which may or may not themselves be atomic. And it says, to the right, a system composed of interacting system elements. And then in the bottom right, there is a much more, much further developed representation of a system, which includes a system of interest with its associated system elements, which 2 of them are systems themselves, and a third one which is a system element. And those systems, those second level systems, if this is level 1 and this is level 2, have their own system elements, which some of those even have their own systems. So a level 3 system, and then a few level 4 systems, and some other atomic system elements, and then finally at the bottom, it's atomic elements. But this goes to show that a system of interest might have various systems beneath them, which may or may not be atomic. And a good example of this might be the way that we use roads in the United States. System of interest is the transportation system, and so one of those system elements might be the actual road surfaces. Then you've got the supporting infrastructure, such as lights, like traffic lights, and those traffic lights might be composed of a support element that actually holds it up, the power system, and then the control system. And the control system might be consisted of a sensor that senses the metal body through some magnetic effects in the ground, and then that might be composed of something else, and you've got other things that control the traffic light. And then the other system would be the actual road vehicles. So it might be cars, buses, and then each of those is its own system. So, you know, a car might have an engine, the chassis, the wheels, the powertrain, and all sorts of other components. It's its own complex system. But that just goes to show that the system of interest, the traffic system, or the transportation system, is a complicated system of systems. So let's go back to the actual text. So this was the hierarchy within a system. Let's talk about the hierarchy within a system is organizational representative system structure using a partitioning relation. The concept of a system hierarchy described in ISO IEEE 15288 is as follows. The system lifecycle processes are described in relation to a system that is composed of a set of interacting system elements, each of which can be implemented to fulfill its respective specified requirements. The art of defining a hierarchy within a system relies on the ability of a systems engineer to strike a balance between clearly and simply defining span of control and resolving the structure of the system of interest into a complete set of system elements that can be implemented with confidence. Urwick suggests that a possible heuristic is that for each level in the hierarchy to have no more than 7 plus or minus 2 elements subordinate to it. Others have also found this heuristic to be useful. A level of design with too few subordinate elements is unlikely to have a distinct design activity. In this case, both design and verification activities may contain redundancy. In practice, the nomenclature and depth of the hierarchy can and should be adjusted to fit the complexity of the system and the community of interest. Section 2.4. Definition of a system of systems. A system of systems is a system of interest whose elements are managerially or operationally independent systems. These interoperating and or integrated collections of constituent systems usually produce results unachievable by the individual systems alone. Because a system of systems is a system in itself, the systems engineer may choose whether to address it either as a system or as a system of systems, depending on which perspective is better suited to a particular problem. The following characteristics can be useful when deciding if a particular system of interest can be better understood as a system of systems. Operational independence of constituent systems. Managerial independence of constituent systems. Geographical distribution, emergent behavior, and evolutionary development processes. Figure 2.2 illustrates the concept of a system of systems. The air transport system is a system of systems comprising multiple aircraft, airports, air traffic control systems, and ticketing systems, which, along with other systems such as security and financial systems, facilitate passenger transportation. There are equivalent ground and maritime transportation systems of systems that are all, in turn, part of the overall transport system. A system of systems in the terms of this description. And here's figure 2.2. Examples of the system and system of the systems within a transport system of systems, reprinted with permission from Judith Dobbin. So you can see the overall transport system, which has a sub-level system of systems. So the transport system is a system of systems, and then beneath that is the air transport system, which is itself another system of systems, which interacts with the ground transport system and the maritime transport system. And then within the air transport system, you've got all of these 5 things that interact with each other and with the external elements of the transport system of systems. So they can get somewhat complex depending on the level of breakdown that you get into. The system of systems usually exhibits complex behaviors, often created by the existence of the aforementioned Mayer's characteristics. Complexity is essentially different from complicated. In complicated systems, such as an automobile, the interactions between the many parts are governed by fixed relationships. This allows reasonably reliable prediction of technical, time, and cost issues. In complex systems, such as the air transport system, interactions between the parts exhibit self-organization, where local interactions give rise to novel, non-local, emergent patterns. Complicated systems can often become complex when the behaviors change, but even systems of very few parts can sometimes exhibit surprising complexity. The best way to understand a complicated system is to break it down into parts and recursively until the parts are so simple that we understand them, and then to reassemble the parts to understand the whole. However, this approach does not help us to understand a complex system, because the emergent properties that we really care about disappear when we examine the parts in isolation. A fundamentally different approach is required to understand the whole in context through iterative exploration and adaptation. As a result, systems engineering requires a balance of linear, procedural methods for sorting through complicatedness, systematic activity, and holistic, nonlinear, iterative methods for harnessing complexity, systemic or systems thinking and analysis. All ways are required when dealing with systems of systems. The tension between breaking things apart and keeping them in context must be dynamically managed throughout the SE process. The following challenges all influence the engineering of a system of systems. Number 1. System of systems authorities. In a system of systems, each constituent system has its own local owner with its stakeholders, users, business processes, and development approach. As a result, the type of organizational structure assumed for most traditional systems engineering under a single authority responsible for the entire system is absent from most systems of systems. In a system of systems, systems engineering relies on cross-cutting analysis and on composition and integration of constituent systems, which in turn depend on an agreed common purpose and motivation for these systems to work together toward complete collective objectives that may or may not coincide with those of the individual constituent systems. Number 2. Leadership. Recognizing that the lack of common authorities and funding poses challenges for a system of systems. A related issue is that the challenge of leadership in the multiple organizational environment of a system of systems. This question of leadership is experienced where a lack of structured control, normally present in system engineering, requires alternatives to provide coherence and direction, such as influence and incentives. Number 3. Constituent systems perspectives. Systems of systems are typically composed, at least in part, of in-service systems, which were often developed for other purposes and are now being leveraged to meet a new or different application from within new objectives. This is the basis for a major issue facing systems of systems engineering. That is, how to technically address issues that arise from the fact that the systems identified for the system of systems may be limited in the degree to which they can support the system of systems. These limitations may affect initial efforts at incorporating a system into a system of systems, and systems commitments to other users may mean that they may not be able to be compatible with the systems of systems over time. Further, because the systems were developed and operate in different situations, there is a risk that there could be a mismatch in understanding the services or data provided by one system to the system of systems if the particular system context differs from that of the system of systems. Number 4. Capabilities and requirements. Traditionally, and ideally, the systems engineering process begins with a clear, complete set of user requirements and provides a disciplined approach to develop a system to meet these requirements. Typically, systems of systems are comprised of multiple independent systems with their own requirements working towards broader capability objectives. In the best case, the systems of systems capability needs are met by the constituent systems as they meet their own local requirements. However, in many cases, the system of systems needs may not be constituent with the requirements for the constituent systems. In these cases, systems of systems engineering needs to identify alternative approaches to meeting these needs, either through changes to the constituent systems or through the addition of other systems to the system of systems. In effect, this is asking the systems to take on new requirements with the systems of systems acting as the user. Number 5. Autonomy, interdependencies, and emergence. The independence of constituent systems in a system of systems is the source of a number of technical issues facing systems engineering of systems of systems. The fact that a constituent system may continue to change independently of the system of systems, along with interdependencies between that constituent system and the other constituent systems, adds to the complexity of the system of systems and further challenges systems engineering at the systems of systems level. In particular, these dynamics can lead to unanticipated effects at the system of systems level, leading to unexpected or unpredictable behavior in a system of systems, even if the behavior of the constituent systems is well understood. Testing, validation, and learning. The fact that system of systems typically are composed of constituent systems that are independent of the system of systems poses challenges in conducting end-to-end system of system testing, as is typically done with systems. First, unless there is a clear understanding of the system of system level expectations and measures of those expectations, it can be very difficult to assess the level of performance as the basis for determining areas that need attention or to ensure users of the capabilities and limitations of the system of systems. Even when there is a clear understanding of system objectives and metrics, testing in a traditional sense can be difficult. Depending on the system of system context, there may not be funding or authority for system of system testing. Often, the development cycles of the constituent systems are tied to the needs of the owners and original ongoing user base. With multiple constituent systems subject to asynchronous development cycles, finding ways to conduct traditional end-to-end testing across the system of systems can be difficult if not impossible. In addition, many system of systems are where was I? Jeez Louise, sorry. I'll start back from here. Depending on the system of system context, there may not be funding or authority for system of system testing. Often, the development cycles of their owners and their original ongoing user base, multiple constituent systems subject to asynchronous development cycles, finding ways to conduct traditional end-to-end testing across the system of systems can be difficult if not impossible. In addition, many system of systems are large and diverse, making traditional full end-to-end testing with every change in a constituent system prohibitively costly. Often, the only way to get a good measure of system performance is from data collected from actual operations or through estimates based on modeling, simulation, and analysis. Nonetheless, the system of systems system engineering team needs to enable continuity of operation and performance of the system of systems despite these challenges. Number 7. System of systems principles. Systems of systems is a relatively new idea, with the result that there has been limited attention given to ways to extend systems thinking to the issues particular to systems of systems. Work is needed to identify and articulate the cross-cutting principles that apply to systems of systems in general and develop working examples of the application of these principles. There is a major learning curve for the average systems engineer moving to a system of systems environment, and a problem with systems of system knowledge transfer within or across organizations. Beyond these general SE challenges, in today's environment, systems of systems pose particular issues from a security perspective. This is because constituent system interface relationships are rearranged and augmented asynchronously and often involve commercial off-the-shelf elements from a wide variety of sources. Security vulnerabilities may arise as an emergent phenomena from the overall system of systems configuration, even when individual constituent systems are sufficiently secure in isolation. The system of system challenges cited in this section require system engineering approaches that combine both the systematic and procedural aspects described in this handbook with holistic, nonlinear, iterative methods. Excuse me. Section 2.5. Enabling systems. Enabling systems are systems that facilitate the life cycle activities of the system of interest. The enabling systems provide services that are needed by the system of interest during one or more life cycle stages, although the enabling systems are not a direct element of the operational environment. Examples of enabling systems include collaboration development systems, production systems, logistics support systems, etc. They enable progress of the system of interest in one or more of the life cycle stages. The relationship between the enabling system and the system of interest may be one where there is interaction between both systems or where the system of interest simply receives the services it needs when it is needed. Figure 2.3 illustrates the relationship of the system of interest, enabling systems, and the other systems in the operational environment. During the life cycle stages for a system of interest, it is necessary to concurrently consider the relevant enabling systems and the system of interest. All too often, it is assumed that the enabling systems will be available when needed and are not considered in the system of interest development. This can lead to significant issues for the progress of the system of interest through its life cycle. And here is figure 2.3, system of interest, its operating environment, and its enabling systems. This figure is excerpted from ISO IEC IEEE 15288-2015, figure 3 on page 13, with permission from the ANSI on behalf of the ISO. And it shows here the system of interest at the bottom left, and then up and to the left there's, or up above them, it's got other systems that it interacts with in its environment, operational environment. And then to the right, it has the enabling systems, which, as it mentioned, are not available all the time, and it's important to not assume that they are. Section 2.6, definition of systems engineering. Systems engineering is a perspective, a process, and a profession, as illustrated by these three representative definitions. Systems engineering is an interdisciplinary approach and means to enable the realization of successful systems. It focuses on defining customer needs and required functionality early in the development cycle, documenting requirements, and then proceeding with design synthesis and system validation while considering the complete problem. Operations, cost, and schedule, performance, training and support, test, manufacturing, and disposal. Systems engineering integrates all the disciplines and specialty groups into a team effort, forming a structured development process that proceeds from concept to production to operation. Systems engineering considers both the business and the technical needs of all customers with the goal of providing a quality product that meets the user needs. INCOSE 2004. Systems engineering is an iterative process of top-down synthesis, development, and operation of a real-world system that satisfies, in a near-optimal manner, the full range of requirements of the system. Eisner, 2008. Systems engineering is a discipline that concentrates on the design and application of the whole, as a distinct from parts. It involves looking at a problem in its entirety, taking into account all the facets and all the variables, and relating the social to the technical aspect. Certain keywords emerge from this sampling: interdisciplinary, iterative, socio-technical, and wholeness. The SE perspective is based on systems thinking. Systems thinking, which is further explained in section 2.9.2, is a unique perspective on reality, a perspective that sharpens our awareness of wholes and how the parts within those wholes interrelate. When a system is considered as a combination of system elements, systems thinking acknowledges the primacy of the whole and the primacy of the relationship of the interrelations of the system elements to the whole. Systems thinking occurs through discovery, learning, and diagnosis in dialogue that lead to sensing, modeling, and talking about the real world to better understand, define, and work with systems. A systems thinker knows how systems fit into the larger context of day-to-day life, how they behave, and how to manage them. The SE process has an iterative methodology that supports discovery, learning, and continuous improvement. As the process unfolds, systems engineers gain insights into the relationships between the specified requirements for the system and the emergent properties of the system. Insights into the emergent properties of a system can therefore be gained from understanding the interrelationships of the system elements and the relationship of these to the whole. Due to circular causation, where one system variable can be both the cause and effect of another, even the simplest of systems can have unexpected and unpredictable emergent properties. Complexity, as discussed in section 2.4, can further exacerbate this problem. Hence, one of the objectives of the system engineering process is to minimize undesirable consequences. This can be accomplished through the inclusion of and contributions from experts across relevant disciplines coordinated by the systems engineer. Systems engineering includes both technical and management processes, and both processes depend upon good decision making. Decisions made early in the life cycle of a system, whose consequences are not clearly understood, can have enormous implications later in the life of a system. It is the task of the systems engineer to explore these issues and make the critical decisions in a timely manner. The roles of the systems engineer are varied, and Sheard's 12 systems engineering roles provides one description of these variations. Go ahead and take a look at these tables while I take a drink here. Alright, so those are Table 2.1, which represents important dates and the origins of systems engineering as a discipline, and Table 2.2, important dates and the origins of SE standards. Section 2.7, Origins and Evolution of Systems Engineering. The modern origins of systems engineering can be traced to the 1930s, followed quickly by other programs and supporters. Tables 2.1 and 2.2 offer a thumbnail of some important highlights in the origins and standards of systems engineering. A list of current significant SE standards and guides is provided in Table 2.3. And then here's Table 2.3. With the introduction of the international standard ISO IEC 15288 in 2002, the discipline of SE, Systems Engineering, was formally recognized as a preferred mechanism to establish agreement for the creation of products and services to be traded between two or more organizations, the suppliers and the acquirers. But even this simple designation is often confused in a web of contractors and subcontractors, since the context of most systems today is as a part of a system of systems. See Section 2.4. Section 2.8, Use and Value of Systems Engineering. Even on its earliest projects, systems engineering emerged as an effective way to manage complexity and change. As both complexity and change continue to escalate in products, services, and society, reducing the risk associated with new systems or modifications to complex systems continues to be a primary goal of the systems engineer. This is illustrated in Figure 2.4. The percentages along the timeline represent the actual life cycle cost accrued over time based on a statistical analysis performed on projects in the U.S. Department of Defense, as reported by the Defense Acquisition University. For example, the concept stage of a new system averages 8% of the total life cycle cost. The curve for committed costs represents the amount of life cycle cost committed by project decisions and indicates that when 20% of the actual cost has been accrued, 80% of the total life cycle cost has already been committed. The diagonal arrow under the curve reminds us that errors are less expensive to remove early in the life cycle. Figure 2.4 also demonstrates the consequences of making early decisions without the benefit of good information and analysis. Systems engineering extends the effort performed in concept exploration to reduce the risk of hasty commitments without adequate study. Though shown as linear, the execution of various life cycle stages associated with modern product development is, in actual application, recursive. Nonetheless, the consequences of ill-informed decisions throughout the life cycle are the same. And this figure is what it was describing. Shows the committed life cycle cost against time. It is reprinted with permission from DAU. All rights reserved. And goes through the stages. You got concept, design, development, production test, and then operations. And as you see, it goes up very quickly, the cost to extract defects relative to at the start. Another factor driving the need for systems engineering is that complexity has an ever-increasing impact on innovation. Few new products represent the big bang introduction of new invention. Rather, most products and services in today's market are the result of incremental improvement. This means that the life cycle of today's products and services is longer and subject to increasing uncertainty. A well-defined systems engineering process becomes critical to establishing and maintaining a competitive edge in the 21st century. As illustrated in Figure 2.5, the development and market penetration of technology has accelerated by more than a factor of 4 over the past 140 years. In this sample of products, the time it took to achieve 25% market penetration was reduced from about 50 years to below 12 years. On average, development from prototype to 25% market penetration went from 44 to 17 years. Two studies have demonstrated the value of systems engineering from an effectiveness and return on investment perspective. These studies are summarized in the following. (2.8.1) SE effectiveness. A 2012 study by the National Defense Industrial Association, the Institute of Electrical and Electronics Engineers, and the Software Engineering Institute of Carnegie Mellon surveyed 148 development projects and found clear and significant relationships between the application of systems engineering activities and the performance of those projects, as seen in Figure 2.6 and explained in the following. The left column represents those projects deploying lower levels of systems engineering expertise and capability as measured by the quantity and quality of specific SE work products. Among these projects, only 15% delivered higher levels of project performance, as measured by satisfaction of budget, schedule, and technical requirements, and 52% delivered lower levels of project performance. The second column represents those projects deploying moderate levels of systems engineering expertise and capability. Among these projects, 24% delivered higher levels of project performance, and only 29% delivered lower levels of performance. The third column represents those projects deploying higher levels of systems engineering expertise and capability. For these projects, the number delivering higher levels of project performance increased substantially to 57%, while those delivering lower levels decreased to 20%. And this is that figure showing project performance versus systems engineering capability. And the earlier market penetration graph is shown here. Section 2.8.1, or it's 2.8.2, excuse me. Systems engineering return on investment. A quantitative research project was completed by Eric Honor and the University of South Australia to quantify the return of investment of systems engineering activities. This project gathered data on 43 survey points and from 48 detailed interviews, each point representing the total results of a single system development project. Projects had a wide variety of domains, sizes, and success levels. Figure 2.7 compares the total systems engineering effort with cost compliance and the schedule performance. Both graphs show that systems engineering effort has a significant quantifiable effect on program success, with correlation factors as high as 80%. In both graphs, increasing the percentage of SE within the project results in better success up to an optimum level, above which additional SE efforts results in poorer performance. The research results show that the optimum level of systems engineering effort for a normalized program is 14% of the total program cost. In contrast, the medium systems engineering effort of the actual interviewed programs was only 7%, showing that programs typically operate about half the level of the system engineering effort. The optimum level for any program can also be predicted by adjusting for the program characteristics, with levels ranging from 8 to 19% of the total program cost. The return on investment of adding additional systems engineering activities to a project is shown in Table 2.4, and it varies depending on the level of system engineering activities already in place. If the project is using no systems engineering activities, then adding systems engineering carries a 7-to-1 return on investment. For each cost unit of additional systems engineering, the project total cost will reduce by 7 cost units. As the median level of the programs interviewed, the systems engineering effort carries a 3.5-to-1 return on investment. And here are the graphs described above. They are cost and schedule overruns correlated with systems engineering effort. And here's the SE return on investment table. This at the top. Alright. Section 2.9. Systems Science and Systems Thinking. This section summarizes the nature of systems science and systems thinking. It also describes how they relate to systems engineering. 2.9.1. Systems Science. Systems science brings together research into all aspects of systems with the goal of identifying, exploring, and understanding patterns of complexity that cross disciplinary fields and areas of application. It seeks to develop interdisciplinary foundations that can form the basis of theories applicable to all types of systems. Example, in nature, society, and engineering. And they are independent of element type or application. Additionally, systems science can help to provide a common language and intellectual foundation for systems engineering and make practical system concepts, principles, patterns, and tools accessible to practitioners of the systems approach. An integrated systems approach for solving complex problem needs to combine elements of systems science, systems thinking, and systems engineering. As such, systems science can serve as a foundation for a metadiscipline that unifies the traditional scientific specializations. The information in this section is extracted from the systems science article in Part 2 of the Systems Engineering Body of Knowledge, or CBOK. Figure 2.8 illustrates the relationships between systems science, systems thinking, and general systems approach as applied to engineered systems. Systems science is an integrative discipline that brings together ideas from a wide range of sources sharing in a common systems theme. Some fundamental concepts now used in systems science have been present in other disciplines for many centuries, while equally fundamental concepts have independently emerged as recently as 40 years ago. Systems science is both the science of systems and the systems approach to science, covering theories and methods that contrast with those of other sciences, which are generally reductionist in nature. Where it is appropriate, the reductionist approach has been very successful in using the methods of separating and isolating in search of simplicity. However, where those methods are not appropriate, systems science relies on connecting and contextualizing to identify patterns of organized complexity. Questions about nature of systems organization and complexity are not specific to the modern age. As John Warfield put it, virtually every important concept that backs up the key ideas emergent in systems literature is found in ancient literature in the centuries that follow. It was not until the middle of the 20th century, however, that there was a growing sense of a need for and possibility of a scientific approach to the problems of organization and complexity in a science of systems per se. Biologist Ludwig von Bertalanffy was one of the first to argue for and develop a broadly applicable scientific research approach based on open system theory. He explained the scientific need for systems research in terms of the limitations of analytical procedures in science. These limitations are based on the idea that an entity can be resolved into and reconstituted from its parts, either materially or conceptually. This is the basic principle of classic science, which can be circumscribed in different ways. Resolution into isolable causal trains, or seeking for atomic units in the various fields of science, etc. Here is figure 2.8, system science and context. Research in system science attempts to compensate for the inherent limitations of classical science, most notably the lack of ways to deal with emergence. System science has developed, and continues to develop, hand in hand with practice, each maturing and learning from the other. And various efforts have taken on complementary or overlapping issues of the new systems approach as progress has been made over time. And these efforts include cybernetics, open system and general system theory, operations research, hard and soft systems thinking, organizational cybernetics, critical systems thinking, system dynamics, systems engineering, systems analysis, and service science and service systems engineering. A broader discussion of contrasts between analytical procedures and iterative systems concepts is provided in Model-Oriented Systems Engineering Science by Hybertson from 2009, from the perspective of the traditional versus the complex systems engineering views of systems. I'll go back up here to this figure real quick to discuss it. So, you've got loops and outcroppings here. So, I guess you can kind of start almost anywhere on this diagram and go around. But say you start with system science. System science studies various system fundamentals and explores and develops theories and methodologies of systems approaches. These theories and methodologies form basis of systems approaches which are applied to engineered systems. Those system scientists have are aware of or active in systems, engineering systems. They're competent in the use of systems thinking, which they apply through systems representations, concepts, principles, and patterns, which they themselves define and evolve. And the information is fed back into itself and further builds system science. Section 2.9.2, Systems Thinking. As a systems engineer, it is vital to develop knowledge and skills that can be utilized in performing a deep analysis of a problem or opportunity situations for which system responses are required. As noted earlier, systems science has contributed to the development of such knowledge. However, during the 20th century, a number of approaches to performing deep analysis has arisen under the title of systems thinking. While it is difficult to put a precise boundary around systems thinking and differentiate it from systems science, many systems thinking methods and tools have become popular and have been successfully utilized in multidisciplinary contexts. Section 2.9.2.1, Systems Dynamics. J. Forrester of MIT developed the Dynamo Systems language and observed that common means of analyzing complex systems could be used in multiple disciplines. Several students of Forrester refined these ideas into methodologies and tools that have provided a useful basis for analysis. Peter Senge, with his popular book, The Fifth Discipline, established systems thinking as a discipline. He also developed the link, loop, and delay language as a means of graphically representing system dynamics. Based upon two primary loops, growth and limit, a number of so-called archetypes have been developed to describe a variety of situations. Another student, Barry Richmond, further developed archetypes by adding flow mechanisms in the simulation languages Stella and iThink, which are commercially available. Subsection 2.9.2.2, Soft Systems and Action Research. Peter Checkland observed that the use of classical engineering approaches to complex problems falls down since there are many soft factors, attitudes, practices, procedures, etc., that affect systems. He also observed that the path to improvement must come through the development and analysis of alternative models. Based upon analysis, discussion, and dialogue, a course of action is planned and executed, and the results observed as feedback for further analysis. John Boardman has been inspired by Checklin's work and has developed a version of the soft systems approach supported by a tool called systemograms. Section 2.9.2.3 Discovering Patterns. Central to systems thinking is the discovery of patterns. A pattern is a representation of similarities in a set of problems, solutions, or systems. Systems thinking captures and exploits what is common in a set of problems and corresponding solutions in the form of patterns of various types as noted in the archetypes described previously. Systems engineers use the general information provided by patterns to understand a specific system problem and to develop a specific system solution. Examples include, but are not limited to, the following. Software design problems, such as adapter. Systems architecture patterns, such as layered architecture and single sign-on. Community or urban design patterns, such as ring road, pedestrian street, and food court. Security and safety patterns, such as fault-tolerant design and role-based access control. Interaction patterns, such as publish, subscribe, and domain-specific patterns, such as the suspension bridge pattern. Pattern categories include domain taxonomies, standards, templates, architecture styles, reference architectures, product lines, abstract data types, and classes and class hierarchies. Another important category of patterns is associated with complex, counterintuitive systems. An example is shifting the burden. When a problem appears in a complex system, the intuitive response is to apply a quick, short-term fix, rather than take the time to develop a longer-term solution. The problem with that approach is that there is often a trade-off between the short-term fix and the long-term solution, such that the initial success of the quick fix reduces the chances that the real solution will be developed. This pattern appears in the typical short-term, long-term priority struggle between the systems engineer, project manager, discipline engineering communities, and other stakeholders within a project. Shifting the burden is one of a set of system archetypes, a class of patterns, sometimes called patterns of failure or anti-patterns, that illustrate the underlying systems pathology behind many barriers to effective systems engineering. Awareness and understanding of these patterns are important for people trying to embed the systems approach in their organization and take positive action to counter these challenges. Additional examples and references are given in the article Patterns of Systems Thinking in Systems Engineering Body of Knowledge. Section 2.9.2.4 Habits of a Systems Thinker. While there are several additional aspects of systems thinking introduced by multiple contributors, the following list summarizes essential properties of a systems thinker. The Waters Foundation, 2013. Number 1. They seek to understand the big picture. Number 2. They observe how elements within the system change over time, generating patterns and trends. Number 3. Recognizes that a system structure, elements in their interactions, generates behavior. And those are emergent behaviors. Identifies the circular nature of complex cause and effect relationships. They surface and test assumptions. They change their perspective to increase understanding. They consider an issue fully and resist the urge to come to a quick conclusion. They consider how mental models affect current reality and the future. They use understanding of system structure to identify possible leverage actions. They consider both short and long-term consequences of actions. They find where unintended consequences emerge. They recognize the impact of time delays when exploring cause and effect relationships. It checks results and changes actions if needed. Successive approximation. People who think and act in a systems way are essential to the success of both research and practice. Successful systems research will not only apply systems thinking to the topic being researched, but should also consider a systems thinking approach to the way the research is planned and conducted. It would also be of benefit to have people involved in research who have, at a minimum, an awareness of systems practice and ideally are involved in practical applications of the theories they develop. For a more thorough description of the discipline of systems thinking, Refer to Part 2 of the Systems Engineering Body of Knowledge, as well as the popular website, Systems Thinking World. Section 2.9.3 Considerations for Systems Engineers. Stillito provides a useful digest of concepts from systems science and systems thinking, organized so as to be immediately useful to the systems engineering practitioner. Properties that are generally true of the sort of systems that systems engineers find themselves involved with are as follows. Number 1. A system exists within a wider context or environment. The context includes an operational environment, a threat environment, and a resource environment. The context may also contain collaborating and competing systems. Number 2. A system is made of parts that interact with each other and the wider context. The parts may be any or all of hardware, software, information, services, people, organizations, processes, services, and more. Interactions may include exchange of information, energy, and resources. Number 3. A system has system-level properties, called emergent properties, that are properties of the whole system, not attributable to individual parts. Emergent properties depend on the structure, parts, and relationships between them, of the whole system and on its interactions with the environment. This structure determines the interactions between functions, behavior, and performance of the parts in interaction of the system with the environment, in ways both intended and unintended. Number 4. A system has the following: a life cycle, a function, which can be characterized following Hitchens as operate, maintain viability, manage resources, or as observe, orient, decide, act. Structure, including the following: a boundary, which may be static or dynamic, and physical or conceptual, a set of parts, the set of relationships and potential interactions between the parts of a system and across the boundary, and behavior, including state change and exchange of information, energy, and resources. Performance characteristics associated with function and behavior in given environmental conditions and system states. Number 5. A system both changes and adapts to its environment when it is deployed, or inserted into its environment. Number 6. Systems contain multiple feedback loops with variable time constants, so that cause and effect relationships may not be immediately obvious or easy to determine. Additional properties that are sometimes true that systems engineers are likely to encounter are as follows. Number 1. A system may exist independent of human intentionality. A system may be part of one or several wider containing systems. A system may be self-sustaining, self-organizing, and dynamically evolving, such systems include complex adaptive systems. A system may offer affordances, features that provide the potential for interaction by affording the ability to do something. Affordances will lead to interactions whether planned or not. For example, the affordance of a runway to let planes land to take off also leads to possibly unintended affordance to drive vehicles across it, which may get in the way of planes, leading to undesirable emergent whole system behavior. A system may be clearly bounded and distinct from its context: the solar system, Earth, planes, trains, automobiles, ships, people. Closely coupled with or embedded in its context: a bridge, a town, a runway, the human cardiovascular system, the internet. A fluid and dynamic makeup: a team, club, social group, ecosystem, flock of geese, and again, the internet. Number 6. A system may be technical, requiring one or multiple disciplines to design, social, ecological, environmental, or a compound of any or all of those. These lists help to explain the needs for systems engineers to think about the system of interest in its wider context so as to ensure they understand both the properties important to the system purpose and those that might give rise to the undesirable unintended consequences. Excuse me, go take a drink here. There's one more section after 210. Systems Engineering Leadership. Many of the processes in this handbook rightly discuss management. Example, decision management, risk management, portfolio management, or knowledge management. And these are all important aspects of the systems engineering process. However, leadership is an equally important topic to systems engineers. In a paper entitled What Leaders Really Do by J.P. Cotter, it states that leadership is different from management, but not for the reason most people think. Cotter describes the key differences between leaders and managers as coping with change versus coping with complexity, settling a direction versus planning and budgeting, aligning people versus organizing and staffing, and motivating people versus controlling and problem solving. A quote often attributed to Peter Drucker is, "Managers do things right. Leaders do the right things." Compare this to the informal definitions of the systems engineering verification and validation processes. Verification ensures you built the system right. Validation ensures that you built the right system. Both verification and validation are important for the development of systems. Likewise, both management and leadership are important for systems engineers and their teams. Different phases of a project demand emphasis on different aspects of leadership. Aspects of leadership that are particularly relevant for systems engineers include thinking strategically and looking at the long-term implications of decisions and actions to set vision and course. Seeing the big picture. Casting or capturing the vision for the organization and communicating it. The systems engineer may be working in support of the identified leader, or sometimes it isn't the leader's prerogative to cast the vision. Defining from the as-is of today to the to-be of tomorrow. Turning ambiguous problem statements into clear, precise solution challenges for the team. Working with the stakeholders, including customers, representing their points of view to the team and the team's point of view to them. Maximizing customer value by ensuring a direct tie of all engineering effort to the customer business or mission needs. Establishing an environment for harmonious teams while working to leverage the potential benefits of diversity, including bridging cultural and communication differences in multidisciplinary teams. Challenging conventional wisdom at all levels. Managing conflicts and facilitating healthy conflict around ideas and alternatives. Facilitating decision-making. Demanding and enabling excellence. Demanding and enabling excellence. Leadership is both an opportunity and a critical responsibility of the systems engineer. The systems engineering leader must have a systems view that takes into account the context, boundaries, interrelationships, and scope. They drive better solutions through the holistic understanding of the problem and its context and environment. Systems engineering leaders highlight the risks of unintended consequences in a proactive manner. Many times, systems leaders need to move the conversation from price and cost to value and return on investment. Systems engineering leaders need to serve as a model for the adaptability, agility, and resilience that is sought in both the systems and the teams that develop them. After all, systems engineering leaders have the best seat in the house for seeing the broader systems view. Section 2.11. Systems Engineering Professional Development. To efficiently and cost-effectively deliver differentiated products to the market, an organization needs to know what gaps exist in their overall capability. An individual needs to know what skills would enable them to be more effective, to develop those skills, and to have a standard to demonstrate and communicate their skill levels. The overall system for optimizing systems engineering delivery is shown in Figure 2.9. Most development, but especially for systems engineering, is achieved through experience and on-the-job training. Typically, 70% of development is achieved through experience, 20% of mentoring, and only 10% through training. Training creates an understanding of basic concepts, while the mentor helps developing systems engineers absorb the appropriate lessons from practical experience. The model in Figure 210 shows how systems engineering development can work for an individual, either pursuing certification or in a development discussion with their manager. INCOSE has developed an SE competency framework built on the work of the INCOSE United Kingdom chapter. Use of the framework can enable employees to analyze their skills and evaluate the need for training, coaching, or new job assignments to fill any gaps found in the assessment. The framework defines 3 classes of competencies and aligns relevant competencies to each class. The classes are systems thinking, holistic lifecycle view, and SE management. The framework has defined 4 skill levels: awareness, supervised practitioner, practitioner, and expert. The framework is tailorable to the needs of the organization. I'm going to go back up here real quick. So here's the systems engineering optimization system, reprinted with permission from Chris Unger, all rights reserved. So I'm not going to try to describe this. I'm not that familiar with this. And down here, it's the professional development system, also from Chris Unger. Alright, section 2.11.1, Systems Engineering Professional Ethics. There will always be pressure to cut corners to deliver programs faster or at lower costs, especially for professions such as systems engineering. As stated in the INCOSE Code of Ethics, the practice of systems engineering can result in significant social and environmental benefits, but only if unintended and undesired effects are considered and mitigated. Part of the role of the systems engineer as a leader and professional is knowing when unacceptable risks or trade-offs are being made, knowing how to influence key stakeholders, and having the courage to stand up for the customers, community, and profession when necessary. The INCOSE Code of Ethics contains sections on fundamental principles, fundamental duties to society and public infrastructure, and rules of practice to help the systems engineering professional in practical applications of ethics to their work and daily lives. Section 2.11.2, Professional Certification. INCOSE offers a multi-level systems engineering professional certification program to provide a formal method for recognizing the knowledge and experience of systems engineers throughout the world. 3 certification levels are available through INCOSE. Associate Systems Engineering Professional, ASEP. Applicants are required to successfully complete a knowledge examination. Certified Systems Engineering Professional, CSEP. Requires a minimum of 5 years of practical systems engineering experience, a technical degree, 3 professional references covering the candidate's cumulative years of experience, and successful completion of a knowledge examination. The Expert Systems Engineering Professional, ESEP, requires a minimum of 25 years of practical systems engineering experience, a minimum of 5 years of professional leadership credits, a technical degree, and 3 professional references covering at least the most recent 10 years of experience. The ESEP award is based on panel review and approval. And that right there is the end of Chapter 2. And again, those sections were 2.1, Introduction, 2.2, Definitions and Concepts of a System, 2.3, the Hierarchy within a System, 2.4, Definition of Systems, 2.5, Enabling Systems, 2.6, Definition of Systems Engineering, 2.7, Origins and Evolution of Systems Engineering, 2.8, Use and Value of Systems Engineering, 2.9, Systems Science and Systems Thinking, 2.10, Systems Engineering Leadership, and finally 2.11, Systems Engineering Professional Development.